Hi, this is my 82nd video on helping people study for Actuarial Exam 2 on Financial Math. Mostly these videos have been about problem solving, but here in the 82nd video I want to take a step back and think especially about what we've been doing recently. Within what's called a Mathematica notebook, this is part of what you see here is a Mathematica notebook in which I can do calculations, enter functions, and make graphs that are actually going to be interactive. And this is going to be what I think is going to be a pretty cool thing, is to see what I drew in the last video, number 81 especially, some graphs. I'm going to make those graphs in this notebook and I'm going to interact with them. I'm going to change some parameters like the loan amount and the force of interest and the number of payments, the number of months, the term of the loan. We're going to make graphs that are related to loans with continuous payment functions where you are saying that you're paying back this loan continuously with a continuous payment stream at a certain number of dollars per month, say, to be specific. You don't need to know Mathematica to appreciate what gets across in this video, but you should have watched the recent videos that I've made, especially videos 77 through 81, where I really talk about this more abstract concept and these ideas to really get what I'm about to talk about. But once you've done that, hopefully this will be really cool and bring things together in a cool way, and we'll see how changing L, delta, and N, for example, change these graphs and why it makes sense. So it's in the context, again, of continuous payment functions. You've got a payback scheme. You've got a certain rate of payment toward paying back the loan in, say, again, dollars per month to be specific, where you pay it off completely over a certain number of months n. Time is in months here. And we've got some functions and we've got some relations. So I'm going to go over these functions that I talked about and these relations that I talked about in video 81. And then after I've gone over that again, I'm going to show you the graphs. Okay? And we're going to try to make sense out of these relations based on the graphs that we make and changing the parameters. What are the functions of interest? First of all, you've got your outstanding balance function, OBT. This notation for the outstanding balance as a function of t is consistent with Broverman's book, The Mathematics of Investment and Credit, 6th edition. This typically, with most payback schemes, is a decreasing function and often is concave down. It has a value equal to L, the loan amount, when time is 0, and has a value equal to 0 when time is n. Its derivative, with respect to time, therefore, since OB is typically decreasing, will be typically negative. I'm calling that derivative OB bar. I actually have not done that to this point, although in video number 81 I did use some other bars over other quantities like you see down here and here, which I'll talk about in a second. This notation for the derivatives with the bar is consistent with the notation in Kellison's book. The 2nd edition of the Theory of Interest is what I use. So that's the derivative. Again, OB is usually decreasing, so therefore OB bar is usually negative in value. You've got your continuous rate of payment function, KT. Actually, if I was going to be completely consistent in my notation, I would call this K bar T to be consistent with this, because this is a rate in, say, dollars per month at which you are paying back a loan. This notation is consistent with Kellison's use, Broverman's use of this idea in Chapter 3 when you've got a continuous payment stream. We can integrate that continuous payment stream, that rate of payment, to get a cumulative payment function, CKT. I'm using, this is really my notation, C standing for cumulative. This is an antiderivative of the rate of change. You're integrating the rate of payment function from time 0 to time t. And this will make it so that the total amount paid at time 0 is 0, since I'm starting this integral at 0. And yeah, it's an antiderivative of the rate of payment. That'll be a function of interest to us. You've got the cumulative interest paid function, CIT, keeping track of the total interest that you've paid from time 0 to time t. It could be thought of as an integral as well, but I'm going to initially just say it's the cumulative interest paid function. Its derivative is what you would then call the rate of interest paid function, I bar t. Again, that's consistent with Kellison's notation as the derivative of this. Again, the C is my notation standing for cumulative. You've got your cumulative principal paid function, CPT. Actually, I make some longer videos on financial math for actuaries where I called this in my 3rd one in that series, CPRT, PR standing for principal repaid, as in Broverman's book. But here I'm calling it just CPT to keep things simple, and its derivative, P bar T, the derivative of the cumulative principal paid, is giving you the rate at which principal is being paid at any moment in time. You've got the relationships among everything here. First of all, the loan amount L must be the present value of the payment stream. Notice that I'm multiplying KT, a rate of payment in dollars per month, say, by the discount factor function. So I'm discounting the payments back to time 0 here. That's the same as e to the negative delta t, where delta is the force of interest. Then you've got this thing here. This is the differential equation that I really paid a lot of attention to, especially in videos 78, 79, and 80, where I solved this differential equation for OB using the method of integrating factors when I was given different things for K. And actually in the last video, number 81, I kind of turned it around. I assumed that OB had a certain form, that it was a linear decreasing function, and I used this equation to actually solve for the rate of payment. I'm calling this again OB bar in this video to be consistent with the other bar notations here. And again, I talked about why this equation made sense. I derived it algebraically and talked intuitively about why it makes sense. If it doesn't make sense to you, you probably should do some reading or go back to, say, starting with video 77 and going through to video 81. And I think if you do that, this equation will make more sense to you, because we'll see some examples as well. There's a similar kind of equation related to the rate of change of the cumulative interest paid function. This derivative is proportional to the outstanding balance. You can also combine these two equations to get this equation, these last two equations there. You can also say, and this should make sense, that at any moment in time, the principal you paid from time 0 to time t, this thing here, plus the outstanding balance should be the loan amount, should be this constant equal to L. If you differentiate both sides of that with respect to time, using the fact that L is constant, you get 0 on the right side. You can get this relationship between these derivatives. You can solve for P bar using this equation and this equation to get this. And you can solve that equation for KT to get what's a pretty intuitive equation. The total rate of payment is the sum of the rates of payments toward principal and toward interest. You can integrate both sides of that equation to get this one using the fact that you want these functions to all have graphs that go through the origin, so you don't need to worry about integration constants being added here. This says the total amount you paid from time 0 to time t is the sum of the total amount you paid toward interest, principal, and the total amount you paid toward interest. Makes good intuitive sense. Furthermore, finally, at time n, you have an outstanding balance of 0. You have a cumulative amount paid equal to the loan amount of principal paid, that is. You have a rate at which money is being paid toward interest of 0 at time n, an instantaneous rate, and the instantaneous rate at which money is being paid toward principal at time n equals the total rate of payment at time n, which is the opposite of the rate of payment toward the balance. All right, that's all the background. Now what we want to do is illustrate these ideas excuse me, in two cases. Same cases as in video 81. You've got a level rate of payment, total rate of payment, which has to be this constant function, equal to L delta over 1 minus v to the n. Again, time is going to be in months here, so delta is really going to be a force of interest that's a monthly force of interest, and v is going to be a discount factor that's going to be a monthly discount factor. N is the number of months. This is a constant rate of payment. And the other example is like in video number 81, the second example, with a linearly decreasing outstanding balance function. OBT here you see is a linear function with a negative slope having a value equal to L at time 0 and equal to, if you plug in t equals n, equal to 0 when t equals n. So we'll consider both of these situations, and we will use Mathematica to enter these functions and change L, delta, and n and see what happens, and illustrate some important concepts. So let's come back up here to the level payment amortization. So I'm entering, first of all, this constant function with this code that you see right here. T is ultimately the variable for this function. These quantities, L, delta, and n, are the things that are the parameters that I'm going to change and make different graphs as I change them. Graphs as functions of T. L is the loan amount, delta is the monthly force of interest, n is the number of months for the term. T is time in months since the start of the payback period. There's your outstanding balance. You could call this equation the retrospective method of the outstanding balance. I could have used the differential equation and solved it as well, but I can use the retrospective method too. I can integrate k to find ck. Let's go ahead and enter this code here. Okay, it is entered now. I did enter it. What I'm going to do first is I'm first going to verify that the differential equation for OB is satisfied. This code right here finds the derivative of OB with respect to t and then simplifies it. What does that equal for this example? It equals this. This code simplifies the right-hand side of the differential equation, delta times OB minus k. We should get the same thing, and we do. These two things are the same. This is verifying that for this kind of situation, the differential equation for OB is satisfied. This code down here will enter the other functions we're interested in, the cumulative principal paid, the rate of change of that function, notice the prime here for the derivative, the cumulative interest paid, and its derivative, notice the prime here. I can enter this code to get those functions, and then I've got this big long chunk of code here. This is going to make the interactive graphs. You don't need to understand how it's working. Let's just go ahead and enter it and use it now. So here we have the graphs, electronic versions of the graphs that I drew in the last video for different values of L, delta, and N. So I've got a loan of 100,000, a monthly force of interest of 0.0025. I got that 0.0025 by taking 3% and dividing it by 12. So the 3% is kind of like a nominal force of interest, annual force of interest. If I divide that by 12, I get an actual force of interest that's monthly of 1/4 of 1%. I got N, the number of months, to be 360 here, which is the same as 30 years. Typical for a payback on a loan that's for a house, a mortgage. Okay, so I got those different values. You see the antiderivatives here, the C functions, the cumulative functions along with OB. The units for these functions would be in dollars. They are functions of time in months. They are antiderivatives. Their derivatives are over here. The bar functions, P bar, I bar, and OB bar, and K itself is a rate of change. The units for these functions would be then in dollars per month as a function of time in months. Just take a look at these graphs first of all to see that it should seem that if you found the slopes of these graphs, you'd get the values of these graphs. For example, the starting point for this payback scheme in this example is that KT in green here is a horizontal line. It's a constant rate of payment over the life of the loan. Its antiderivative going through the origin would be this green graph then. That's the integral. It's the cumulative area under the KT graph from 0 up to whatever time you're talking about. It's straight with a positive slope, the slope equal to the value of KT. Notice that the value of CKT, the total amount you paid by time 360, is higher than the total loan amount. The loan amount is 100,000. That's this dashed line here. CK is above that by the end, which it should be because you're paying interest. What else do we see? The other function we focused on for the most part a lot is the OB function. Excuse me. Again, with the typical kind of payback scheme, this function is decreasing and concave down is what you see here. Its derivative, therefore, is negative because it's decreasing, and in fact, the derivative itself is decreasing because this graph is concave down. You see the OB bar graph is negative and decreasing. You see the cumulative principal paid is this red graph here. You can see that the red and blue graph add up to the dashed horizontal line at 100,000. That's illustrating this fact right here, this fact that CPT and OBT add up to the constant function at L. The blue and red graphs, if you will, are reflections across the horizontal line. That's half the loan amount here. Also notice CPN is equal to the loan amount. By time n, by 360 months here, this graph is up to the dashed line. The principal paid is the entire loan amount by time n. And then this purplish, dark purple kind of graph, CIT, that's the cumulative interest paid function. Its derivative I bar t is over here. Notice this is increasing and concave down, so I bar is positive and decreasing. And in fact, the slope at time 360 at time n is 0, just like I bar of 360 is 0 down there. Notice also that P bar heads up to kt by time n. The red plus purple here must equal the green in these derivatives. That's illustrating this equation right there for those derivatives. Okay, the fact that the purple and red add to the green here. That's what I did highlight. Yes, that's what I highlighted there. All right, now let's do what my main goal here is, and to change these parameters, to change L, delta, and N. Let me first change L, because that's the simplest thing. Watch what happens as I increase the loan amount. Move the slider to the right. All these graphs go up, as they should. Your loan amount is going up. You're going to pay more overall. But the general properties still stay the same. OB of N is 0. CP of N is equal to the loan amount. CKT goes above the loan amount. Okay, it's also true that CIT plus CPT equals CKT. You can see that visually there. So the loan amount goes up, the graphs go up, and the derivatives get further from 0 as well. What about if I increase delta for fixed L and N? That's increasing the force of interest per month in this case, which corresponds to increasing the interest rate overall, the nominal effective compound interest rate, if you will. Watch what happens here. I'm going to increase it. It seems like mostly it's changing the purple and green graphs. However, it actually is changing the red and the blue too. You can see it now here as you go more extreme. As delta increases, certainly the purple and green graphs, the cumulative interest paid function and cumulative total paid function go up. And their derivatives over here go further from 0. That's illustrating the fact that if the interest rate gets higher, you pay more interest. Okay? CPT still ends up equaling the loan amount by the end, but the total cumulative interest, CIT, goes higher. And in fact, if delta is high enough, in this case higher than about 0.045 or so, with this particular L, you end up paying more than the total loan amount, which sounds bad, right? You're paying a lot of interest over the life of the loan. That's actually pretty typical with home loans, mortgages, where you're paying back over 30 years. In most situations, you actually do end up paying more in interest than you borrowed to begin with. If you change the term of the loan, I'm going to decrease N in this case. Watch what happens again. CIT and CKT go back down this time. When you pay it back for a shorter amount of time, even if the interest rate is higher, even if delta is higher, the total interest paid is less. And the total cumulative amount paid is not as much above the loan amount. Okay? So this is illustrating some important conceptual points. What else is being illustrated with the red and the blue graphs? If delta is real small, the red graph is almost straight, the blue graph is almost straight. If delta is big, the red and blue graphs become less and less straight. Their concavity gets more extreme, you might say. Okay, so that's illustrating these functions in the typical context. Let's also spend a little time illustrating these functions in this not typical context where you're assuming OB is a linear decreasing function. So I'm going ahead and entering OB right there, and I'm finding I bar with this equation. K, the rate of payment, I'm going to essentially use that differential equation, and I'm going to integrate it to find CK. Here's the form for K in this example. It's a linear decreasing function. You can see a function of t. Its antiderivative would then be quadratic, I guess. Yeah, you can see a t squared there. Is the differential equation for OB still satisfied? Yes, but the derivative is different because OB is different. It's a constant. There's the derivative, and the right-hand side of the differential equation does simplify to the same thing. Here are the other functions being entered, and here we can also confirm that CP at time n does equal the loan amount L. All right, now let's make the graphs in this context. So for this context, what's different? The graphs are basically pretty similar, except there are some differences. No matter what L, delta, and N are here, OBT is a straight line. going down. Therefore, CPT is also straight, going up. Those have to add to give you L, the loan amount. We still see that CIT is increasing in concave down and has a slope equal to 0 at time n. And CKT is increasing. However, with the typical payback scheme, CK was a straight line. Here, with this kind of payback scheme, the total amount that you pay over time is increasing in concave down, and its derivative is still linear, but is a decreasing linear function here instead of a horizontal function, instead of a constant function. The same general things happen if I increase L or delta. Watch, I'll increase L, the graphs go up. If I increase delta, the amount of interest you pay goes up. Notice here, though, that the red and blue graphs don't change with this scheme, whereas they did with the other scheme, if delta changes. The red and blue graphs stay the same with this kind of payback scheme, but the purple and green graphs change. And just as before, if n changes, even if I'm at a spot where here you're paying more interest than you borrowed, if I decrease the term of the loan, watch, the purple graph does go back below the loan amount over here. So once again, even with this kind of payback scheme, if you make the term of the loan shorter, a smaller number of months, you are going to pay less interest, less than the loan amount, for example, like with car loans that are typically 3 or 4 or 5 years. So I hope you've enjoyed this video. It's been fun for me to make. You don't have to understand the Mathematica code if you don't want to, but maybe this would inspire you to learn how to use Mathematica if you have it available for you. But it illustrates some really cool things, I think. So I'll get back to problem solving in the next video.